A large proportion of the anthropogenic carbon is being stored in the atmosphere, and we're going to take a look at changes in atmospheric CO2. Critical processes in the carbon cycle respond to environment at multiple timescales. What this means is that if we're going to understand the carbon cycle at the global scale and the changes that occur in atmospheric CO2 concentrations, we're going to have to look at multiple different processes that are operating at different timescales. We have to think about daily cycles, annual cycles, and decadal cycles, if not even longer cycles. Now we know that pre-industrial, before the Industrial Revolution, CO2 concentrations were approximately 280 ppm. And again, you'll often see this abbreviated as ppm or ppmv, which means parts per million by volume. And again, often when I talk about this, we'll just say ppm. So 280 ppm for CO2 concentrations pre-industrial. In the past, if you go back relatively far, it's been as high as 3,000 ppm. So there's times when CO2 concentrations have been a lot higher than they are in the modern era. On geological timescales, what controls CO2 concentrations? Well, it's primarily the weathering of silicate rocks. So calcium silicate is shown here, and that reacts with CO2 and water to form calcium carbonate, silicon dioxide, CO2, and water. And this is the weathering process. So you can see we started with 2 units of CO2 and ended up with 1 here. And it's a process, this weathering of calcium silicate rocks is a process that consumes CO2. So half this, approximately 1 unit of CO2 is consumed for every unit of calcium silicate that's being weathered. There's a lot of calcium silicate out there, and weathering consumes a lot of CO2 on geologic timescales. So the consumption of CO2 by weathering can be huge. In addition, on geologic timescales, we have burial and sediments. It's a relatively slow process at any one point in time, but it accumulates, and on longer timescales, it's significant fluxes. In addition, there's volcanism, and volcanism releases CO2 into the atmosphere. But all of these factors, all of these fluxes, are relatively low, and the response of things like weathering are too slow to influence the current trajectories. It's just not going to be the amount of weathering that we expect in the next 50 or 100 years is not going to change current trajectories of CO2 concentration increases in the atmosphere. Now at the millennial scale, there's differences in solar input that occur, and that drives differences in productivity. So we can see here that there's variations in temperature and CO2 concentrations in Antarctic cores. And a lot of these patterns, on the x-axis we've got age, which is in thousands of years, and here's CO2 concentrations. And CO2 concentrations going up and down, for example, are driven by inputs, solar inputs, differences in outputs from the sun, and differences in the distance from the Earth to the sun. There's also biological amplification that can happen. So there's feedbacks that occur that increase or decrease, well, in this case, increase CO2 uptake more than what you'd expect just based on the differences in solar input. So for example, the transport of dust can increase ocean productivity. So times that are dry, for example, we've got dust that will leave the terrestrial environment, enter the ocean, and fertilize the oceans. In addition, vegetation is going to respond on millennial timescales, and that's a factor that can also impact CO2 concentrations on these longer timescales. The balance for all of this is relatively uncertain, though. We know that CO2 concentrations are relatively stable pre-industrial. Here, these are graphs of CO2 concentrations, methane concentrations, and nitrous oxide. This is time, this is going to be years, so we're looking over the past millennia for all of this. And here's CO2 concentrations. They were relatively stable, and then only recently did they start to go up. Again, the CO2 concentrations are coming from air that was trapped in ice cores. These were taken from Antarctica, as well as from direct atmospheric measurements during the modern period. So we've got roughly 280 ppm, and for almost 800 years it was relatively constant, and then we see this exponential increase that's happened since then. Methane concentrations, we had looked at a 10,000 year, actually 15,000 year time slice before. Now we're just taking a look at the past 1,000 years, and they were relatively constant, 750 ppb instead of ppm, and they've shown an exponential increase too. CO2 concentrations in 2011 were approximately 390 ppm. In 2013, atmospheric measurements of carbon dioxide had reached 397 ppm, and spot measurements, as you'll see, routinely exceed 400 ppm. Mauna Loa numbers for atmospheric CO2 concentrations will soon reach 400 ppm within a couple years. That's really the highest concentration that we've seen in the past 20 million years. So all of this additional 7 or 8 petagrams per year of carbon that we're putting into the atmosphere, and the 4 petagrams that's being stored there each year, has led to the highest CO2 concentrations in the past 20 million years.